Okay, so just to pick up where we left off, and I'll do a example, sort of a long example that involves most of the things that could that might come up when you do one of these Fourier series expansions or figure out the Fourier series for a function. I'll do one that's, like I said, a little tricky. Some of the easier ones where it's just a constant, you'll get nicer integrals and stuff. But anyway, sort of as usual, I wanted to show you a tougher example so the other ones won't seem so bad. So this, I won't give much of a recap since you just watched this video, but I will transfer over, or I won't actually, but you all can, since you have this in your notes, transfer over that in order to, so what we're about to do is I'll give us a function, a little f of x, and we're going to see if we can come up with the Fourier coefficients, right, or the Fourier expansion, or the Fourier series. Many different names all mean the same thing. In other words, will we be able to compute these AMs and BMs and all of those guys? And the answer is yes. And we're going to see something I think pretty neat when we do this. So for sure, the computational things we need are what are in these three boxes. So the three formulas we're going to use in a minute are this one, and then these two. Right? Oh, I should have said that for n greater than or equal to 1. So we'll use those and see if we can get all these characters. So who's our big winner, our function that we're going to spend the next half an hour or so trying to figure out the Fourier expansion, or Fourier series for? So let's look at, oops, I don't have a pen. So let's examine what's usually known as the Sawtooth function. So you know you're in for a treat when a function has a cool street name that the people refer to which is Sawtooth, and you'll see why in a second. So the Sawtooth function is this function. I'll draw you the graph maybe first, and then I'll give you the math version. So if you let me give myself a little more space here. It doesn't matter what interval you do this on. I'll maybe just choose -2 to 2, just to make it nice and easy. So we're going to do L equals 2 for this. Sorry, my line's not in the middle there. Then the then the Sawtooth function is one that simply makes a tooth. So I'm going to give you a color here, blue. So the Sawtooth function is the one that would come down here from, so this point is -2, 2, and this point is 2, 2. Now, you might say that doesn't look like a saw. I don't even know what a sawtooth is, but it looks a little more just like a V. But in order to make this possibly in order to make this a periodic function, the Sawtooth function is born when you take this one V and you just copy it over and over and over again. So now this isn't necessary for doing the problem. It just does a better job of sort of explaining where the name came from. Okay, well, give this one more up, I guess. So, okay, if you squint hard enough at that, that looks like the teeth of a jack-o'-lantern or something like that, right? Or the mouth of a shark or something like that, or at least the upper. And if I drew another one in down here, it would look more like a mouth, I guess. But so this is known as the Sawtooth function, and it's simply just lines, right? I don't have anything fancy here. So if we want the piecewise definition, which I guess we will use because we're going to do some calculus with this, then who is this Sawtooth function? Sorry, I should have kept with blue here. So I could say, well, if I'll just do the original V that I did. So I'm on the line y equals -x if I go down, and then I'm on the line y equals x when I go back up. So I will be on -x if, or for x between 0, for x between -2 and 0, and I will be on positive x if x is between 0 and 2, right? Okay, so that just describes these two line segments. Oops, I don't know how that got all. So that just describes this line here and this line here. And then, of course, in order to make this the sort of full sawtooth function, we make it periodic. So then we say, oh, okay, and how do I get the whole graph here? Is, of course, we would copy this graph. With period 4. By that, of course, I mean the length of one cycle is 4. All right? So it's period with length 4, so we're going to do an L, since we're going -2 to 2. So the period is 4. And if you want to just remind yourself, that means L is 2, because we're going to do -2 to 2 here. Okay, so our goal is to figure out the question here, what are we, aside from drawing some pictures here, is what's the Fourier series, or the Fourier's expansion, or however you want to say that, for the sawtooth function. We're going to do it between -2 and 2, right? So we're not going to, you obviously don't need to actually copy this to infinity both ways. So just one period of it is plenty. But of course, well, what we come up with will work, because it's going to be based on sines and cosines. I'm not ruining the surprise by telling you that, because we already saw it. So actually, without even having to try, since we're going to end up with sines and cosines in our answers, it's going to repeat forever and ever and ever, right? So again, just sort of before we launch into a bunch of fancy math, just bare bones with our hands, what are we trying to do? Is we're trying to take these teeth here, and we're trying to say, could that be a sine and cosine function, or some combination of sines and cosines? I mean, before we even get into this, it already a little bit looks like sine and or cosine. Maybe I might say that looks a little more like sine than cosine, perhaps, although only because it goes through the origin, right? Sine goes through the origin, cosine doesn't. Well, it's already got this sort of pattern that it might, I mean, it's not crazy to think that we could figure out some way to get sines and cosines to line up pretty well. And I'll show you a graph at the end that's going to show you just how well our work here is going to, how close it's going to come. Okay, so here we go. We wanted to find the Fourier. Okay, great. So it's this awful thing. Oh, here I am. So of course it's this. It's this, right? So this is the Fourier series definition. So I need to be able to figure out A0. That's the number that's going to go here. I need to figure out and I need to figure out the A's, AMs, and the BMs, and then I can put them all together and get an actual just regular old function, and we'll see what it looks like. All right, so I'm going to use these formulas. Oh, I don't have all these extra slides here. So I'm going to use these formulas to figure out what all of these missing pieces are. So let's start with the easiest thing first. So let's compute A0. So to get A0, you can look back over here. So to get A0, I'm going to do this guy. Right, I'm going to do 1 over 2L. For us, L is 2. So I'm going to do 1 over 4, right, 1/4, integral -2 to 2 of the function. So 1 over 2, here, I'll just do it that way. So you see, right, so L is 2. Right? So 1 over 2L, great, integral -2 to 2 of the function. Well, we did these in calc something. When you have a piecewise function, right, I have to split it up. I have to split the integral up into which rule am I following at various times. So I'm going to do that. That's 1/4. Right? So I have 1/4, and I have, let's see. So I can't really go from -2 to 2 because I have different behaviors, whether I'm on this side or whether I'm on this side. Right? So the cute way to do this is to say, well, let me go -2 to 0, and then I'll go 0 to 2. Because between negative 2 and 0, this behaves like negative x. And between 0 and 2, it behaves like positive x. Okay, now these are super easy integrals, so let's just do them. So of course here I get negative x squared over 2. And I have to plug in negative 2 and 0. And then this one, of course, I get x squared over 2, and I have to plug in 0 and 2. Okay, so I have 1/4, and let's see, I plug in 0 and I get 0, of course. I plug in negative 2 and I get 4 on the top and 2 on the bottom, which feels like 2. But it's, oh, sorry, I got 0 for the first thing. And then I have minus negative 2. And on this side, I end up with, when I plug in 2, I get 4 divided by 2 is 2, minus 0. So I think that looks like 2 plus 2, also known as 4, and then 1/4 gives you a big 1. Okay, so we've figured out that A0 is 1. So in this expansion, we at least know that the numerical piece, the thing that doesn't have sines and cosines, is just 1. Okay, great. So that's easy. Now we have to do the part that's a little harder, and by harder I just mean because it involves doing some calculus. Not that it's understanding-wise any harder. But how about the AMs and the BMs then? So let's see. So let's start with the AM. So if I want to do I just want to copy the formula exactly so that I'm not confusing you. So we're going to do AN, I guess, right? N. So we're going to try to figure out who's AN, and well, it's this. So I'm going to write this down. 1 over L, which for us is 2. So 1/2, negative 2 to 2, our function, and then cosine of n, remember that's actually n pi over L, x. Okay? So I'm going to write this down. So copy this over. So 1 over L, negative L to L. Okay. Our function, and then cosine of nx, which for now I'm going to refill in what that is, because I am actually going to do some math with this. So remember, the cosine subscript n really means n pi over L, and for us L is 2. Okay, so I got to do this. So that's my goal for the next, I don't know, probably 10 minutes, is to figure out how much is that. Okay, so cosine, that's not too scary. I can deal with cosine. But f of x, well, that's my sawtooth. So once again, I have to split this up into 2 pieces, because in this case, I shouldn't make you think it's always the case you have to split it up into 2 cases, right? These things. Right, the 2 intervals. If you have a function that doesn't have this sort of weird up and down behavior, if it's just consistent, then you could just do one integral. You don't always have to split it. But I do in this case because, again, my function is defined piecewise. This is me trying to do a harder example. But if you have an easier example, just do it, right? But I can't, right? I gotta do this. So so I'm going to say, all right, well, first of all, I'm already tired of doing the 1/2. So how about I multiply that to the other side, and we'll deal with that 1/2 at the end, right? Okay, so so instead of going negative 2 to 2, I'm going to go negative 2 to 0, and then 0 to 2, just like we did in the last one. And the reason being that I can then say, oh, from negative 2 to 2, this behaves like negative x, f of x, right, is negative x cosine. And 0 to 2, on the 0 to 2 side, it behaves like regular x. Okay, so I'll just do this. So you see me, right? So it was negative x there, obviously. Probably that's not bad to pull that negative out in front. And so what you, of course, maybe notice is that I, of course, have the same integrand here. Oh, my goodness, sorry about that. 0. I have the same integrand, right? So I only have to do this integral once. It's just that for this one, my bounds are -2 to 0, and for this one, my bounds are 0 to 2, right? And this one obviously has a negative in front of it. So at the very least, I don't have to do 2 of these. I can just do this integral once, and then I'll evaluate it everywhere I need to. Okay? So let me just point at this one since it has lots of free space under here. Can you do this integral? Of course you can. You got to, dust off the cobwebs a little bit, but in this, you're all math majors, so I know you know how to do integration by parts. And of course, if you remember, the idea of integration by parts maybe says that in order to pick the right candidate for u versus dv, trig is always the least favorite thing for u, right? It's, what is it, L-A-T-E? Oh, I guess E. E is the worst. But T, trig, that's the next to worst. X is not bad at all. So for this, I would choose X for u. dv is this cosine stuff. Oh boy, I can fit that in there. Yeah. Okay, and then you end up, of course, writing down your v and writing down your du, neither of which is all that hard. Well, okay, it's 1. If this is dv, then of course to go up to v, it's going to turn into sine, and then I have to do the reciprocal of that. Okay, so I'm going to abbreviate integration by parts just because I don't want this to get super long in terms of just me writing stuff down. But could you complete integration by parts? I hope so, right? Remember, it's u times v, so it's this times this, minus the integral of v du. Well, look, you're already in good shape because, right, du is just 1. So the integral of v du is one you're going to be able to do. All right, I don't want to do this whole thing, so I'm going to just cut to the what do you get when you finish this integral. All right. So if you do this, what we end up with is, so it's a little bit of a mouthful here, so I'll jot it down though. So you get 2x over n pi times sine of n pi over 2x. And then the other piece you get is 4 over n pi squared cosine of n pi over 2x. Okay, so that's what you get when you do the integration by parts and you chase it around and combine the like terms and blah, blah, blah. You get that. Now that's the integral of this, right? That's the antiderivative, I should say, of that. Okay? So now, of course, what do I have to do with that? Well, I actually have this in 2 places, right? I've got to plug in, I have to take the negative version of this and plug in 0 and -2. And then I have to take the positive version of this and plug in 0 and 2. All right, so I'll at least show you the pieces, and I'll at least talk you through it. At this point, again, this is literally arithmetic and algebra, so I'm not going to show you every single step here, but you should be able to plug stuff in and get what I'm getting here, right? So this is the integrand here, or this is the antiderivative here. So now, of course, I have to take this, and I have to take this, and I have to plug in x equals 0 at x equals 2. That's going to be, move my arrow over. That's going to be to get that answer. Now to get this answer, I'm going to have to take the same antiderivative, and I have to plug in x equals -2 and x equals 0. Now, of course, normally I would do them in that order. I would, don't write this down yet. I would do that, right? And I would do that. but there's a negative in front of this. So either I could rewrite this with the negative distributed and do that. But remember, what's the difference between doing positive, throwing a negative sign? The only thing that's going to change, or a slicker way for me to do this, is to actually just plug the bounds in reverse order. Because if you think about it, that's going to, instead of me doing b minus a, I'm going to do a minus b, which is exactly accounting for the negative sign. Okay, so if you don't like that cute trick, then take another line or two to distribute the negative to this and plug in -2 and 0. Fine. But this will work the same way, right? So I just have two. I hope this notation isn't super crazy. So I'm going to take this, and I'm going to do 2 rounds of plug-in. I'm going to do 2 and 0 and do my usual subtraction. And I'm going to do -2 and 0 and do my usual subtraction. Okay, and again, I swap those to account for that negative. Okay, so let's do this, and we'll see that actually a lot of this stuff cancels. So, so when I do x equals 2, so here I'll try to kind of label that. This is me doing x equals 2. Let's see. Well, what do I get? I'm going to get, when x equals 2, I'm going to get 4 over n pi. Now when x equals 2, I get sine of n pi. Okay, I'm not done yet though, because I got to do this piece too. So when I do this piece over here, I get 4 over n pi squared. And when I plug in x equals 2, I get cosine of n pi. Okay, so that's my x equals 2. Here, maybe I'll do it below. Okay, so I'll ask, or if we were together, I would ask somebody to tell me something smart about this, but we'll, well, anyway, we'll ponder something smart about that anyway. Okay, so I'm 1/4 of the way done, so I did that. Now what am I going to do now is I would do subtract what I get when I plug in 0. Okay, so let's see. Well, this one we can see is actually going to be, I'm just going to throw some parentheses around these just for style, really. So now let's try x equals 0. Well, right off the bat, we get a break, because when I plug in x equals 0 to the first piece, that's 0. And when I plug in 0 over here, I don't get 0, but let's say I get 4 over n pi squared. And I get cosine of 0, also known as 1. Put a 1 there just so you remember that that came from doing cosine of 0. Okay, that's pretty good. So I'm done with 2 out of the 4. Okay, moving on. On the second piece now, and I'm just going to keep throwing this stuff together, I have another top and bottom to do. So when I plug in the top here, let's see, what do I get? So I do x equals -2. So of course now I would have -4 over n pi sine of -n pi when I do x equals -2. And then over here, I'd have 4 over n pi squared again. And then here I'd have cosine. When I do x equals -2, I get cosine of -n pi. Okay, that's my x equals -2. And then I'm going to cheat a little bit here and say, what's my last term? Is I have to now subtract, but it's the same one, right? X equals 0. So I'm just going to say subtract, sorry, I thought I'd have a little bit of space to squeeze that in there. But subtract your x equals 0 case, which happens to be right here. All right, so we're going to do several things right now. We're going to clean this up. I'm going to go to a new slide since I need more space. And we're going to see if we can simplify this greatly, which we will. Okay, so actually, you know what? I'm going to squeeze one more line in here so that we can see all the pieces falling in place. So let's see. So sine, we know sine and cosine have nice, tricky, not tricky, but have cute behaviors. So maybe I get something cute to happen here. So sine, remember, n's a whole number. N's 1, 2, 3, 4, 5, whatever. sine of any multiple of pi, you have to think back a little bit here, I guess, right? But sine of any multiple of pi is 0. So this is actually, so in fact, sine, wherever it appears in any of these, is always going to be 0. So this first term here, that's just 0. And for cosine of n times pi, remember, n's a whole number, 1, 2, 3, and so on. Now you have to think for a minute about the cosine graph. Okay, well, let me leave that one alone for a minute. Okay, we'll do this on the next slide. So I get pi squared, and I get cosine. So just copy that down again. Okay, so that's the first piece. Second piece, so now I have 2 of them. Right, because I crammed it in here, right? But I actually have 2 of these, and they're both minus, right? So I could really say minus 2, right? That one and that one. And I don't have much here, right? I have 4 over n pi squared. Also known as 8 over n pi squared, which is what we'll write on the next slide. Okay, but again, 2 of them, because you have 2, you have this one and that one. Okay, and then at the end here, I similarly have a sine term, sine of any multiple of pi, any whole number multiple of pi, even negative multiples of pi, whole numbers, are still 0. And similarly over here, cosine, now here's where, so I have 4 over n pi squared. Now, cosine of negative n pi, I could write that down, but now here's where I will say, but let's notice something cute about cosine. I will remind you with a cosine graph up here in the corner. Oh boy, that's worst cosine graph ever. So notice here I have cosine of n pi, and here I have cosine of negative n pi. But now here's where if you look at the graph, you can maybe remind yourself, if I'm cosine of somebody, let's call that x, cosine of negative x is, hello, I'm not super level there, but it's exactly the same. Right, so the cosine graph, if you might remember, is symmetric about the y-axis. So cosine of negative n pi is exactly the same as cosine of n pi. All right, so that's symmetry. Okay, so when I go to write this on the next slide, I'm going to do one more simplify, which is that looking at all this stuff, I don't have much here actually. This is exactly the same as this. So I have 2 of them. So I have 2 of these and 2 of these. So, believe it or not, we are left with 8, right. Right, 8 of those. Oops, went the wrong way. Right, 8 of these and minus 8 of these. Okay, and so obviously I could divide by 2 to get that an. And in fact, why don't I factor that out? Oops. Oop, and it's not 8 anymore. If I divide by 2, of course, now that's 4. So I could factor that out, of course, and I just have cosine of n pi minus 1. Okay, so we're getting somewhere, So, okay, now let's just make one last clever observation before we really write down a punchline here. Now, cosine of n pi, remember, n is 1, 2, 3, 4, it's whole numbers. So I'll again remind you, cosine graph here. I'll try to make this one a little more accurate. Okay, so that's pi, that's 2 pi, 3 pi, 4 pi, That's -1, and that's 1. So that's the cosine graph right there. So, and in particular, now n pi, I don't know how much n is, but obviously it's a whole number. So notice from my graph here, of course, when n is odd, like at 1 pi, 3 pi, and so on, cosine is -1. When n is even, cosine is +1. So let's look at this. When n is even, this is going to be 1, which means I'm going to have 1 minus 1, also known as 0. And so the a even terms are all going to be 0. On the other hand, when n is odd, like pi, 3 pi, 5 pi, and so on, cosine is -1, which means this will turn into -2. And this will turn into -8, which is obviously not 0. Okay? So I think a nice way to represent our answer here would be to say, so who are these ANs? Well, AN is either 0 if n is even, or, right, so if it's even, and that's again because cosine of an even pi is 1. Blank, which would clear that out, right? Or, if n is odd, this is -1 right here, which means you get -2, which means you get -8. Okay, and I'll say because cosine of an odd pi is -1. I'll draw a similar arrow so you know where I'm pointing you to. Okay, so oh my goodness, after 20 minutes and a lot of calculus, what are we left with now? So an, which are these coefficients, all the even ones aren't even there. They're all zeros. And the odd ones, well, I mean, this isn't my favorite formula, but it's not awful. 8 over n pi squared. Okay, whatever. So when n is 1, I have 8 over pi squared. When n is 2, when n is 2, I have nothing. When n is 3, I'd have -8 over 9 pi squared. Okay, and so on and so forth. Okay, so when you deal with these problems, you're often going to reach this point here, where you say, okay, so these are my things. Great. And if you can present them in a nice sort of, usually you often get an even and odd sort of thing. You don't always necessarily get 0 for one of them, but a lot of times this is the sort of behavior you get. All right? So I'm going to say a few concluding things and then show you a neat picture. So let's take a deep breath and say, so where are we now? So we figured out A0. Check. We now figured out AN. Check. Now if I go back through and redo this whole thing, there was also the BNs. But because BN is going to involve us doing this with sine here, rather than cosine, right? So in order to do the BNs, I will do all of this work again, but with sine here. Because of the fact that it's sine, when you do these integrals, you're going to get 0 for all of them. I'm not going to do that out because I don't want to do it, but I promise if you repeat this entire process, but put a sign here instead, you're actually just going to get literally everything is 0, not just in the even and odd cases, right? So I'll just say, if you repeat this whole process for the BNs, you'll actually get that BN is 0 for all n's. In other words, you don't have any b's, which are the sign pieces of the expansion. Okay? So I don't want to, like I said, I'm not going to do that out. But if you did it, I promise you'd end up with that conclusion. So what do we have then? So pulling this all together, so the Fourier series for the Sawtooth function we started with is, so let's put everybody together. So A0 turned out to be 1. Okay, and then the cosine terms with the ANs, oops, here we are. The ANs turned out to be, you get something in the odd cases, but you get nothing in the even cases. So I'm just going to write out a few of the odd terms here. So when n equals 1, what's our formula? You get negative 8 over n pi squared. Okay? So I would get, when n equals 1, I'd get negative 8 over n, which is 1, pi squared. And remember, these are the coefficients of our cosine n terms, which remember that's n, which is 1, pi over L, x. Okay, so that's the n equals 1 term. Okay, I'm just going to jot a few down. Now I don't have an n equals 2 term because it's even. So if I go over to the n equals 3 term, I'd have negative 8 over 9 pi squared cosine of 3 pi over 2. Okay, that's n equals 3. I'll just do one more. And then negative 8 over 25 pi squared cos 5 pi over 2x. Okay, and now I'll just put some dots at the end there. All right, stylistically, if this drives you crazy, having plus, negative, you could, of course, switch those to minus signs if you want, but I'll leave them like that so you can see where they came from. Oops, sorry, and that's the n equals 5 case. Okay, if I'm throwing anybody off with the why is this pi over 2, 3 pi over 2, 5 pi over 2, just go all the way back to what we started with. So remember, the A's that we just did all that work to get, they go with cosine of n. We've switched over to n's instead of m's, right? But cosine of nx, remember, cosine nx is really cosine of n pi over L. N pi over L. N pi over L. Right? So if n is 3, 3 pi over 2. 2 is L. If n is 5, 5 pi over 2. N pi over 2. Okay, pi over L. Okay, so that's why those numbers change a little bit each time. Whew, so deep breath and conclusions are coming now. So this, now, I mean, this is not anybody's favorite thing to look at. Agree. However, let me make one comment and then I'm going to show you a neat graph. So first of all, let's notice as n gets bigger, right? So of course this is n equals 1, n equals 3, n equals 5. So obviously as if I dotted, so I didn't have to keep writing. But as n goes down the line, what's happening to an? Remember, those are the coefficients. That one, that one, that one, and so on. Well, either by looking at the 3 we just wrote down, or if I go back a slide to the previous example, you can all tell me, hopefully, that as n gets bigger, these coefficients, as n gets bigger, these coefficients are going down to 0. In fact, rather quickly, because I'm squaring and I'm multiplying by pi. So probably after about 6, 7, 8, or maybe 10, maybe let's say, when I get to n equals 10, for example, this is a very minuscule number. Which means if I'm trying to say how close did I come, pretty darn close, because at that point you're not adding very much in, because the coefficient of the 10th term in this is like 0.000001. Okay, so at that point, who cares? Just leave it off. All right? So in particular, notice, as n goes to infinity, these coefficients are actually heading towards 0. Meaning, it's okay. That's an awful arrow. It's okay to cut it off. at some point. Since you're essentially adding 0, or let's say you're adding almost nothing, as n increases. Okay, so that's good news, right? So in terms of a practical, somebody might use this for something. Well, that's good to know that you don't have to go on forever. That would be tragic. Okay, so again, if you took numerical analysis, you kind of remember this was the idea with power series also, is that eventually they essentially just vanish. So that's good. But a last thought is, okay, so here's this cute sawtooth function. We didn't know what that looks like. It looks like our blue graph from the beginning. There it is. So if I'm claiming that this monstrosity that we came up with approximates the sawtooth function, I might say, well, gee, does it? I mean, I can't just eyeball and say, sure it does. So what would happen if I graphed that? So I did a few plots here. I did this in MATLAB, but these are just regular functions. You could graph them in your calculator if you want. And I just graphed a few of them for you. So first of all, the original sawtooth was supposed to be this. Okay, because this is the origin right here. Sorry, you know how MATLAB graphs don't have axes on them, right? But this is 0, 0. And this is -2, 2, and that's 2, 2. Right? So red is that's the sawtooth, or one tooth of the sawtooth, I guess. So what did I plot for you here? Maybe I'll take my graph off just so you can see it a little bit better here. Is that I plotted 3 versions of this. So all I plotted for you actually here, the blue one, the wavy guy here, that's literally just these first 2 terms. So that's 1 minus 8 over pi squared cosine of pi over 2x. Right? So just those 2 alone, just those 2, is the blue graph. So I'll try to label that for you. So right, so that's with 2, just the first 2 terms, you get the blue graph. Now it's a little hard to see because it's under stuff, but I mean, I missed a little bit on the ends, but it looks like a rounded tooth anyway. Okay, well, if I go to 3 terms or 4 terms, those are my 2 gold graphs here. So I'm not gonna try to separate those 2 because they look awfully similar, right? But the other 2, this is me doing 3 and 4 terms in the expansion. That's how I got those 2, and then actually the one on top is actually the 4 term. So that's me graphing this, right? Me graphing this whole thing, essentially, right? Or I did one with just the first 3 and one with these 4. Okay. But just after 4 terms, I get pretty darn close. Let me put the red back in here to our original sawtooth. I'm pretty close, right? So I don't know. I mean, I would say, in case you were like, you're never going to be able to use sines and cosines to approximate something. Well, we just did, and it's pretty darn close. All right? So aside from this being a fun trick and thing to do, this will lead us then, you're going to do this exact process, not just for fun like we did in this example, but on the initial temperature profile in order to solve the heat equation. Okay, so you're welcome to experiment a little bit. I will put some problems up for you to look at. I'll do one heat equation solution from start to finish, so that you have one to look at, but it's just doing this. So I've sort of shown you everything you need to know at this point. So, okay, sorry I went over a little bit there. But have a wonderful weekend, and I will, as usual, be in touch next week.